Hi everybody, this is our last lesson in Unit 2. And in this unit, I'm going to focus on some other trigonometric forms for integrals. And these ones you're going to see involve some trigonometric identities, not any that are kind of out there or ones you've likely seen these before in some way, shape, or form. And I'm only focusing on 3 trig identities. Okay, so I'm not going to expect you to look at a table of 40 trigonometric identities and figure out the right one. The 3 that we're going to focus on are sitting right here in this slide, and they'll be in later slides as well as you need them. Okay, so the integral that we're going to look at is if we have sine x and cosine x, and they are to some exponent. Okay, example here being sine cubed of x cosine squared of x. And how do we go about solving them? And what we do is we use trigonometric identities. The 3 that I have listed here, the first one, sine squared x plus cosine squared x equals 1. That's actually quite a well-known identity. The next 2 are similar versions. 2 times cosine squared of x is equal to 1 plus cosine of 2x, okay, not the exponent 2, okay, so that means it's cosine, and then within the brackets, it's 2x, versus this one, okay, that's the equivalent of cosine of x all squared, okay, so that's the difference between those two. Same thing goes with identity number 3, 2 sine squared of x is equal to 1 minus cosine of, again, 2x. Remember, the 2x is here in brackets. Okay, so there's 3 different cases that we're going to solve with this type of integral. And it's going to depend on whether the exponents are odd or even. So if you have one odd and one even of each type, or they're both even. Okay, so I'm going to present you 3 different cases, and we're going to use these trigonometric identities and then the method of substitution, which we've talked about already in this unit, to solve the final form you're going to see. Okay, so our first case is going to be if we have the sine function has an odd exponent and the cosine function is even. So going back to our last slide, we had the integral of sine cubed of x cosine squared of x dx. So when we say m and n, m is the exponent for the sine function, and n is the exponent for the cosine function. So if m is odd, okay, that means that in this case we have 3, which is an odd number, and cosine is 2, so it's an even number. So what we do in this case is remember we have rules of exponents. Okay, so if we had some exponent, let's say we had 3 squared times 3, that's the same as 3 to the exponent 2 plus 1, or adding the exponents of each of these. So we can do the opposite of that, and in this case we're saying we have sine cubed of x. Well, we can write that as 2 sine functions multiplied together. In other words, sine squared of x times sine of x. Okay? Because if you were to multiply these 2 together, you would get sine of x to the exponent 2 plus 1, or the exponent of these. When it doesn't have an exponent here, you assume that it's 1. So what we do is we essentially are just rewriting it, and you'll see why in just a second. So if we do that, okay, we remove 1 from the 1 exponent, so we're left with sine squared of x times sine x instead of sine cubed. Okay, if you multiplied these 2 together, you would get back to your original function here. Okay, so that's all we've done so far, is rewrite this expression. So now, with that rewritten expression, what we can do is we can take this sine squared of x term, and we can use the first trigonometric identity that I showed here. Sine squared of x plus cosine squared of x equals 1. If you were to rewrite that, you would have to move the cosine squared of x to the other side. So we're left with sine squared of x is equal to 1 minus cosine squared of x. Okay, so I'm going to substitute in 1 minus cosine squared of x instead of sine squared of x. Okay, so what we're left with is 1 minus cosine squared of x multiplied by sine x and cosine squared of x dx. So we had to rewrite this term so that we had a sine squared of x that we could substitute. Okay, and the reason for that is now that we have a 1 minus cosine squared of x, we can multiply this out, right? If we multiply it out, we get 1 times sine x and cosine squared of x. Okay, so that just becomes sine x cosine squared of x dx. Minus, we have cosine squared of x multiplied by sine x and cosine squared of x. So what that means is we'd have sine of x multiplied by cosine squared of x, and then cosine squared of x again. Remember, you can add the exponents together. So we'd have cosine of squared of x times cosine squared of x becomes cosine to the exponent 4 of x, adding those exponents. So we can rewrite this in the following form. We have the first term, sine x cosine squared of x dx. And remember, since we have addition or subtraction in this case, in between them, we can write them as separate integrals. So that means the second piece becomes minus the integral of sine x times cosine to the exponent 4 of x. Okay, so now we have two terms that what you'll notice the key factor is here, one of the terms does not have an exponent. In other words, it's to the exponent 1. Okay, and that is important for when we're solving the integral. Okay, the reason it's important is now we can use the method of substitution to solve for each of these integrals. Okay, so I'm going to do them. I'm going to split this in half, and I'm going to do them both separately using the method of substitution. Okay, so we can first rewrite each of these integrals. In this case, it's the integral of sine x times cosine of x squared dx. The second one is the same as cosine of x to the exponent 4. I forgot the integral sign. Actually, here, I'll rewrite it so you can see the integral sign. The integral of cosine of x to the exponent 4 sine of x dx. So this looks just like when we did integrals, okay, using the power rule. All right, and if we did that, it was always the function that was raised to an exponent that we used as the function u. Okay, so I'm going to do substitution on both of them. We'll start with the first function on the left here. Okay, I'm actually going to make this a little smaller because we're going to have to put the final answer together. So on the left, I'm going to let u equal cosine of x. So du by dx is equal to negative sine of x. Or solving for just du is equal to negative sine x dx. So we're close here, right? We have a sine x and a dx. We need that negative to not be there. So we divide both sides by negative 1. So we get negative du is equal to sine x dx. Okay? If we substitute those in, we then get the integral of u squared times negative du, right? So using the power rule, remember the integral of some function to the exponent n is equal to that same function to the exponent n plus 1 divided by that same exponent n plus 1. So if we do that, we'll move this negative outside and we'll simply do the integral. So we get negative u to the 2 plus 1 divided by 2 plus 1. In this case, we'd have plus a constant, but we'll add the constant at the very end when we're done the integral. So if I substitute in the integral here, or the function for u, what we get is negative cosine cubed of x divided by 3. okay? So it becomes simpler when we break it up so that one of these terms, again, is to the exponent 1. The second integral, again, using the substitution rule, I'm going to let u equal cosine of x. Du is equal to negative sine x dx. You can see where this is going. The same as the first integral. So we want to have just sine x dx. So we divide both sides by negative 1. And we get negative du is equal to sine x dx. Substituting all these values in, we then get the integral of u to the exponent 4 times negative du, which means the integral here becomes negative u to the 4 plus 1 divided by that same exponent, 4 plus 1. Okay? Substituting in the value of u, we get negative 1 over 5 times, in this case, cosine. We can write it as cosine 5 of x, or negative 1 over 5 cosine x to the exponent 5. Either way is correct. All right? So you do each of those two integrals separately, and then you can just simply combine them, all right, and write the answer. So what that becomes is the first integral, negative 1 over 3 cosine cubed of x, minus the second integral. So we have minus negative 1 over 5, which becomes plus 1 over 5 cosine 5 of x. And then at the very end, you can add the constant. You don't have to be doing the constant kind of throughout your integration process. Okay? So these different cases, this is the first case of 3 I'm going to show you. They're all in an attempt to get it into a format where you can integrate it easier, whether it's through the power rule, method of substitution, etc. Okay? The second case is the opposite of the first case. And in this case, n is odd, or in other words, the exponent for the cosine function is an odd number, while the exponent for the sine function is an even number. Okay? So in this case, we're going to do the exact same thing. We're going to take the cosine function and we're going to subtract 1 off its exponent. And by doing so, we have to add a cosine x function. So that when we multiply these two together, cosine squared of x and cosine x, we would arrive at the same value here, cosine cubed of x. So the first step is exactly the same. The second step, again, looks very similar. The difference is we use the same trigonometric identity, okay? But instead, we are going to solve for cosine of x. In other words, what we're substituting in is that cosine squared of x is equal to 1 minus sine squared of x. So in other words, we brought the sine function to the other side of the equation this time instead. So if we substitute that in, we get 1 minus sine squared of x times the remaining terms, sine squared of x and cosine x dx. So just like in the first case, we can now break this up into two integrals. The first integral being 1 times the remaining terms, which gives us just sine squared of x cosine x dx. And the second one, okay, multiplying sine squared of x by the remaining terms, gives us minus sine to the 4th of x times cosine of x dx. Okay? So you can see there was a similar pattern there, right? We're left with one of our functions here being to the exponent 1. In this case, cosine. In the first case, we had sine of x being the function to the exponent 1. So everything we're doing in this case is simply the reverse of the first case. So now again, we can use the method of substitution to solve for both of these. And what I'm going to do this time, all right, is you can see both of them have a cosine of x dx. The same thing happened in the previous case. But what I want to show you is rather than doing a method of substitution separately for both, you can actually do just the one method of substitution and substitute it in for the entire integral, so both integrals, okay? So if we do that, in this case, we have sine squared of x and sine to the fourth of x, which you can rewrite this integral as the integral of sine x squared cosine of x dx minus the integral of sine of x to the exponent 4 cosine of x dx. Okay? If you do that, all right, remember, I always take the term that's inside the brackets, or in other words, raised to an exponent, usually, as the function u. In this case, they both have the same function inside. That's why we can do substitution just once. So I'm going to let u be sine of x dx, which means du by dx is simply cosine of x. And now solving for just du, we're going to multiply both sides by dx. And they'll cancel on the left-hand side, so du becomes cosine of x dx. So now the difference is I'm going to substitute this value of u and du into both integrals. Okay? If we do that, we get the integral of u squared du, right? Because we substituted in du for cosine of x dx and u for sine x, minus the integral of u to the fourth times du. That's a bad d. So now we can use the power rule to solve for each of these. And what we get is we get u to the exponent 2 plus 1 divided by the same exponent 2 plus 1 minus u to the exponent 4 plus 1 divided by 4 plus 1. Okay, and then again plus a constant. We can put that in at the very end. So now substituting in u, what we end up with is 1 over 3 times sine cubed of x minus 1 over 5 sine the exponent 5 of x plus a constant. Okay, so we only had to do the substitution once. Okay, you could also apply that method if you look at the first case. Okay, but I wanted to show you it in the first case the way you had seen method of substitution done in the past. So our third case is if neither of the sine or cosine functions have an odd exponent. In other words, both the exponents for sine and cosine are even. So our example here is sine squared of x and cosine squared of x. So two they're both even numbers. So in this case, we're going to use the other two trigonometric identities that you see listed in this table. 2 cosine squared of x equals 1 plus cosine of 2x. Keep in mind that the difference between these is cosine squared of x is actually cosine of x all squared. Cosine of 2x is actually the cosine of 2x. Okay, so 2x is the function within the cosine. Okay, and what this means is it's 2 times the function x that was sitting here in this cosine squared function. Okay, so it doesn't have to say cosine squared of x here. Okay, it could be another function as long as you do 2 multiplied by it. So the same thing happens for the sine function. 2 sine squared of x is equal to 1 minus cosine of 2x instead of plus. Okay, to use both of these trigonometric identities, we just want cosine squared of x and sine squared of x. So we have to divide both sides by 2. Okay, and if we do that, these identities look like cosine squared of x is equal to 1/2 times 1 plus cosine of 2x, and sine squared of x is equal to 1/2 times 1 minus cosine of 2x. So we're going to substitute both of these in, one for the sine squared of x and one for the cosine squared of x term. Okay, so I've color-coded them so you can see which one I substituted where. Okay, so for the cosine squared of x function, I substituted 1/2 times 1 plus, okay, cosine of 2x. And for the sine squared of x function, I inserted 1/2 times 1 minus cosine of 2x. Okay? So next we've done a couple of steps here. The first is I've removed the constants from the integral. So I have the 1/2 and the 1/2. Multiplying those out gives us 1/4. Then in the bracket, I've actually multiplied these out, remember, using FOIL. So the first terms, 1 and 1, gives us 1. The outside terms, 1 and positive cosine of 2x, give us positive cosine of 2x. The inside terms, negative cosine of 2x and positive 1, gives us negative cosine of 2x. And our last terms are negative cosine of 2x and positive cosine of 2x. That gives us negative cosine squared of 2x, okay? Because you're multiplying the two of them together. So another fact I'll note here is you notice we have a cosine 2x minus cosine of 2x. So those two terms actually cancel out. So we're actually only left with the 1 minus cosine squared of 2x. Okay? So rewriting that, okay, we have the term with the 1 and the term with the cosine squared of 2x. So we can split that into two integrals. The first one being the 1/4 times the first term. Remember, our integral was 1/4 times the integral of 1 minus cosine squared of 2x dx. So I've split this into two integrals. Okay, 1/4 times the integral of the first term, which is just 1, minus 1/4 times the integral of the second term, which is cosine squared of 2x. Okay? So now with that, you can see we're starting to get to easier integrals. The integral of 1 dx, okay, is an easy integral. The second term, in order to get it to that, we have to use the same trig identity that we used here. And that was the 2 cosine squared of x equals 1 plus cosine of 2x. In this case, remember when we had it written, we had cosine squared of x was equal to 1/2 times 1 plus cosine of 2x. Now remember what I said. The x term here, it doesn't have to just be x, okay? It's cosine of some function. In this case, we're cosine of 2x. So what that means is this is actually cosine squared of 2x is equal to 1/2 times 1 plus cosine of 2 times this function here, which is 2x. Okay? So I've actually written it in like that. Okay? So it doesn't just have to be x there. That's the important factor to consider here. So if I do that, I substitute in 1/2 times 1 plus cosine 2 times 2x, that actually is cosine of 4x, okay? Because you're just simply multiplying those two constants together. So now, again, we can do a couple things. First, we have the integral of 1/4 times the integral of 1 dx. That doesn't change. But the second one can now be broken up into two integrals. So we can move the 1/2 out of the integral. And what we have there would be 1/4 times 1/2, which would actually be 1/8. So now we have minus 1/8 times the integral of the first term here, which is just 1. Minus, in this case, again, 1/8 times the integral of the second term, which is now cosine 4x dx. Okay? So now we're left with three integrals that we can simply do ourselves. Okay? The first two are integration of just dx, so that just becomes x. The last term, we'll do it using substitution. Okay? And in this case, we'll have u is equal to 4x. Okay? So in other words, the item inside the cosine. So du by dx would just be equal to 4. Okay? Or in other words, multiplying both sides by dx, we get du is equal to 4 times dx. Okay, remember we don't have a 4 here, just a dx. So to remove that, we have to divide both sides by 4. So what we have is 1/4 du is equal to dx. Okay, so now moving to our next steps, we can substitute that in. And while we're doing it, we might as well solve the first two integrals. So this becomes 1/4 times x minus 1/8 times x, okay, minus 1/8 times the integral of cosine u times 1/4 du. Okay, so now what we can do is we can actually, again, move the 1/4 out of the integral. So what this becomes is 1/4 minus 1/8 is simply 1/8 times x. This becomes minus 1/32 times the integral of just cosine of u. Okay? So what we're left with in our final answer, therefore, is 1/8 times x minus 1/32 times the sine of u, or in other words, the sine of 4x. Okay? So again, what we're doing is breaking down the integrals into more manageable pieces that are easier to integrate. Okay? So now that we've covered all three cases, we're going to walk through one example before going to the final piece of this lecture. So this is evaluate the integral of sine to the exponent 4 of 4x, cosine to the exponent 5 of 4x. Okay? So what we see here is that the sine function has an even exponent. The cosine function has an odd exponent. So remember, the one with the odd exponent is the one that you're going to have to use the trigonometric identities on. Starting with that, remember our first step was to subtract 1 from that exponent. In other words, rewrite it as two cosine functions. So if we do that, we get this becomes the integral of sine to the exponent 4 of 4x, cosine to the exponent 4 of 4x, multiplied by, remember, that same function, cosine of 4x. Because if you multiplied these two terms together, you would arrive at cosine to the exponent 5 of 4x. Okay? So now remember, our trigonometric identity we had, oh, that's in blue, I'll switch it back to red, was sine squared of x plus cosine squared of x is equal to 1. So in this case, what I'm going to look at here is the cosine to the exponent 4 term. Remember, that's what we did last time. We always tried to get that to an even number, and then we did it. So if we solve for cosine, in this case, cosine squared of x is 1 minus sine squared of x. But something's wrong here. This is to the exponent 4. Okay? Well, in order to make these an equivalent piece, right, we can rewrite this integral as the integral of sine to the exponent 4 of 4x. And this could actually be cosine squared of 4x all squared, right? Remember, if you have some number or something a to the exponent m, and that's raised to the exponent n, that's the same as multiplying them together. Okay, so in this case, if you have cosine squared of 4x squared, that's the same as cosine of 2 times 2, okay, multiplying the exponents, or cosine to the exponent 4 of 4x. Okay, so knowing that, I'm rewriting, all right, I'm going to erase this to give us some more space. I'm rewriting that second term in this form. Okay, so to finish it off, we have cosine of 4x dx. So that means I'm going to substitute in this trig identity here. Okay, and if I do, I get the integral of sine 4 of 4x times 1 minus sine squared of x, all squared, cosine of 4x dx. Okay? So now that I have that, remember, in order to expand this out, I'm going to have to use FOIL, okay? Because what that actually is 1 minus sine squared of x times 1 minus sine squared of x, okay? What I missed here is, remember, this was 4x, so this actually should have been 4x, okay? Meaning that these were sine squared of 4x and sine squared of 4x, okay? Remember, these are, that was a mistake. I made that mistake, obviously. On a test, that's one of the reasons I get you to show your work, right? Because that's a simple substitution error that's very simple for you to make. But come later on, I will only remove a small amount of marks if that's your only mistake, okay? So sorry for that, but a learning opportunity, I guess. So now using, again, FOIL, we can multiply this out, and we get our first terms. 1 times 1 is 1. Our outside terms, 1 times negative sine squared of 4x, okay, is negative sine squared of 4x. Our inside terms, negative sine squared of 4x times 1, again, minus sine squared of 4x. And our outside term, or our last term, sorry, negative sine squared of 4x times negative sine squared of 4x is positive sine to the exponent 4 of 4x. Okay, again, adding these exponents together. Okay? So if we simplify this, we get 1 minus 2 times sine squared of 4x plus sine to the exponent 4 of 4x. Okay? So this is going to look very long, okay, when I substitute this in, but then we'll simplify it out and you'll see that it'll end up with multiple integrals that we know how to solve for, okay? So if I substitute that in, I get the integral that equals the integral sine to the exponent 4 of 4x cosine of 4x, and then substituting everything in the brackets, 1 minus 2 sine squared of 4x plus sine to the exponent 4 of 4x dx. Okay? It will simplify out to easier integrals. I know that this looks like a lot. Okay? So I'm going to multiply each of these out. Okay? So in other words, into each of these terms. And if I do that, I get the integral of, okay, what I'm going to do is multiply it out and then divide them up in integrals, into multiple integrals, okay, because we have a minus and a plus here, okay? It's because they're added or subtracted from one another. So our first one is the sine to the exponent 4 of 4x, cosine of 4x multiplied by 1. So we're left with just sine to the exponent 4 of 4x times the cosine of 4x dx. The second one, we then have, I'll do them each in different colors, minus. For the second term, we have sine the exponent 4 of 4x times cosine of 4x. And that's multiplied by this negative 2 sine squared of 4x. So what we have here is minus, first we have that constant, 2, times the integral of, we have sine to the exponent 4 and sine squared. Multiplying those together gives us sine to the exponent 6 of 4x, and then our cosine 4x dx. And our last term, okay, removing our notations we've made so far, we have sine to the exponent 4 of 4x times sine to the exponent 4 of 4x. So plus the integral of sine to the exponent 8 of 4x. And then we have the cosine terms, cosine of 4x dx. Okay? So what you can see, as complicated as that looked, we have 3 distinct integrals, each of them with one term, yet again, to the exponent 1, and the other term, again, being the sine term, having an exponent. So the exponent 4 here, 6 here, and 8 here. Okay? So we're left with the same thing. Again, what you're going to see is your final answer, you're going to be able to use the method of substitution once that will satisfy all three of these. So I'm going to write out that final version we had from the last slide, okay, which was the integral of sine to the exponent 4 of 4x cosine of 4x, okay, minus 2 times the integral of sine to the exponent 6 of 4x cosine of 4x, plus the last integral, sine to the exponent 8 of 4x cosine of 4x dx. So again, I'm going to use the method of substitution because we can write all these integrals as the integral of sine of 4x to the exponent 4 cosine of 4x dx minus 2 times the integral of sine of 4x, again, all in brackets to the exponent 6 cosine of 4x dx, plus our last integral, sine of 4x to the exponent 8 times the cosine of 4x dx. Okay? All of them have the same sine of 4x term, all raised to, in this case, different exponents. But we can still use the method of substitution for it. So what I'm going to do, I'll do it up on the top right here. We're going to let u be the term in the brackets, sine of 4x. So du by dx is going to be cosine of 4x, and then multiplied by the derivative of the term in the brackets here, okay, for cosine, which is 4. So again, in each of these terms, we have a cosine 4 of x and a dx. We do not have the 4. So the two steps we have to do here, first, we'll solve for du, and we'll do that by multiplying both sides by dx. And we get that du is equal to 4 cosine of 4x dx. Now, we don't want that 4 there because then we can't substitute them in directly here. So we divide both sides by 4. And what we get is 1 over 4 du is equal to cosine 4x dx. Okay? So now we have the u and the du terms to substitute in for all three integrals here. Okay? So what we're left with is the integral now of u to the exponent 4 times 1 over 4 du minus 2 times the integral of u to the exponent 6 times 1 over 4 du plus the last term, the integral of u to the exponent 8 times 1 over 4 du. So now I'm going to move the constants outside of each of these before doing the integral. So if I do that, I get 1 over 4 times the integral of u to the exponent 4 du, minus, I have 2 times 1 over 4, which is 1 over 2, times the integral of u to the exponent 6 du, plus the last term, 1 over 4 times the integral of u to the exponent 8 du. Okay? So now for all of these, we can simply use the power rule. Okay? And if we do that, we get 1 over 4 times u to the exponent 4 plus 1 over 4 plus 1 minus 1/2 times u to the 6 plus 1 divided by the same exponent, 6 plus 1, plus 1 over 4 times u to the 8 plus 1 over 8 plus 1. Okay? If I simplify those, I get 1 over 4 times 1 over 5 is 1 over 20, u to the exponent 5, minus, in this case, I have 1 over 2 times 1 over 7, which is 1 over 14, u to the exponent 7, plus 1 over 4 times 1 over 9 is 1 over 36 u to the exponent 9, and then plus a constant. So our final step is now we can simply substitute in sine of 4x, or what our value was for u. And if we do that, we get 1 over 20 sine of 4x to the exponent 5 minus 1 over 14 sine of 4x to the exponent 7 plus 1 over 36 sine of 4x to the exponent 9 plus a constant. So this was a very long example, and the reason for that is as these exponents both become larger, there just ends up being more terms. The method of solving it is always going to be the same. Okay, it's just there was more work in that we end up with additional terms. You can see now our final answer has 4 terms if you include the constant versus 3 in the previous one. Okay. So our last item to talk about in this lesson is we're going to look at inverse trigonometric functions. Okay, and remember, we'll do sine and we'll do tangent. So the derivative of the inverse sine function, if it was sine inverse of some function u, was 1 divided by the square root of 1 minus u squared times the derivative of that function u, if it was something other than just x. Okay, in this case, I had our times du by dx. If we have a constant, in other words, the function is sine of inverse of u divided by some constant a, the derivative is very similar. Okay, the difference is you actually have, instead of 1, you have that constant a, and it becomes a squared instead of the term 1. So you can see in the original function it was 1, and now here it's a squared. Okay, the reason that's important is you might have the integral of some function, 1 divided by the square root of a number that's not 1 here, minus u squared. Okay, and if you do that, it simply ends up being the inverse sine of that function u divided by that constant value a. Okay. The same thing applies for the tangent function. So remember, the derivative of tan inverse of a function u was 1 over 1 plus u squared without, so no square root sign, times du by dx if that function u is not just x. So when you have, again, that same function, but it's u divided by some constant a, then instead of it being 1 divided by 1 plus u squared, it's 1 divided by that constant a squared plus u squared. And because it's the tangent function, the difference is you also have an additional 1 over a term. So I'm going to show you where these are applied in 2 examples. Okay, but looking at it, if you have the integral of 1 over some number a squared, could be 2 squared, 3 squared, 7 squared, whatever, plus that same function u squared, you can write it, if you took the integral of 1 over a times the inverse tangent of that function u divided by a. Again, these are formulas I'm going to provide you, but again, you'll be recognizing these patterns in these questions. Okay, so let's look at 2 examples. You're probably going to look at them and think, wow, we just did previous cases in this lecture that took so long, and these ones are going to be such a fast 2 integrals. First one is 1 over the integral, or evaluate the integral of 1 divided by the square root of 16 minus x squared dx. Okay, so remember when I talked about the sine function, it was 1 divided by the square root of a squared minus u squared. So it looks oddly similar to that, right? In this case, a squared is equal to 16, so that means a must be equal to 4. And the term u squared is equal to x squared, so that must mean that u is equal to x. Okay, just taking the square root of both. So remember, the integral of a function that was like this, 1 over the square root of a squared minus u squared, was actually equal to the inverse sine of the function u divided by a plus a constant. Well, now we know what u and what a is. So this integral simply becomes substituting those in. So the integral then becomes the sine inverse of u, okay, which is x, divided by 4, plus a constant, okay? So in this instance, you can see recognizing the pattern, similar to how you did when you're recognizing patterns using tables. Okay, so in their previous lesson, using integration by use of tables, the same thing is applying here. All right. Our second example is evaluate the integral of 1 over 4 plus 9x squared. Again, instead of the sine function, you remember the integral of the tangent function. So 1 over some constant a squared plus u squared was equal to 1 over the constant a times tan inverse of u over a plus a constant. So in this case, we have the same form. So a squared must be equal to 4, or a is equal to 2. And u squared must be equal to 9x squared if it's following the same format, which means that u must be equal to the square root of both these terms. So the square root of 9 is 3, and the square root of x squared is x. So u must therefore be x. So knowing this, we can now simply plug and play these terms in. And what we're left with is 1 divided by a, which is 2, times tan inverse of, in this case, u, which is 3x, divided by a, which is 2, plus a constant. Okay? So recognizing that format allows you to quickly solve for these. Okay? So that was everything for this class. This is the last lesson for Unit 2. So again, I recommend you try these practice problems. The first examples we did with multiple cases will take you a little more time to solve, but you'll start to get a little quicker at them with the more examples that you do. If you have any questions, feel free to send me an email, and I guess that's it. Thanks, everybody.